Move on now to the supplied side of regolith, metal extraction from regolith, and we'll have a break at 13:50 at about an hour and 20 minutes from now. The first one up we have, of course, go in any order that people are available, but Elliot, you are the first one up. And Andrea, you can remind me if Ellie's driving or if you're driving.
I believe Elliot is driving his own slides.
That's what I think so too.
I can drive.
Fantastic. Thank you. So as a reminder, 10 minutes. I asked Andrea to give you a bing at 9 minutes, 30 seconds. We have a little bit of flexibility in the time, but please don't take too much advantage of it due to one person being unable to make it. Jonathan Geifman came ill, so he will not be presenting today from Helios. All right, Elliot, if you would, please lead away.
Yeah, quick mic check.
Good to go.
All righty. Thank you, Carl, and the APL team for facilitating this. My name is Elliot Carroll. I'm the CEO of Lunar Resources. Lunar Resources is a space industrial company funded by the US government and partner with leading space commercial companies to develop scalable technologies to industrialize space. And specifically for this discussion, we are developing technologies to perform large-scale resource extraction of metals from lunar regolith. I guess to start off, discussing what the business cases are or why you would want to do that. We generally categorize the reasons why you would want to utilize in-situ metals on the moon for three main reasons. Number one, some things will never make economic sense to ship from Earth. And Mark McDonald mentioned that when he was talking about structures. Number two, some things can just be made better in space, specifically functional materials or thin film materials. And number three, you need to repair things in space, especially surface infrastructure. And frankly, it's becomes a lot less expensive when you are able to do that in situ. So Lunar Resources now for a number of years has been developing a process called Molten Regolith Electrolysis to turn lunar soil into raw commodities or constituent commodities. This Molten Regolith Electrolysis, it's a high temperature electrolytic approach to break down the oxides into their constituent elements. There are various ways to operate this technology. You can do it in continuous mode, you can do it in batch mode, you can do it in a semi-continuous mode or semi-continuous batch mode. And there are various reactor designs of how to operate such processes. However, it's mainly all these systems involve effectively having an anode and a cathode in a reactor, putting in lunar soil, and then striking a current between the two to break down those materials. And to operate molten regolith electrolysis systems, I'll just call that from now on MRE. So to operate MRE systems, you only need lunar soil and electricity to extract out a range of different metals from the lunar soil. Our process that we're developing is focused on extracting out high purity aluminum, iron, magnesium, and silicon. And as a byproduct, we actually also extract out oxygen, which we collect and then purify with a program that we're partnered with NASA on. As well, the various leftover slag materials can also be used and casted into various ceramics and other glass on the moon. The reason, I should mention, the reason why we selected molten regolith electrolysis a number of years ago is fourfold. Number one, MRE does not use any consumables from Earth, so it's very economical. Number two, it's lunar soil agnostic, so we can use regolith from the highlands, we can use regolith from the mare. All we need is a metal oxide material to run our process on. Number three, it is, relatively speaking, highly electrically efficient for resource extraction technologies. As you're trying to scale up your production rates, power becomes really the main factor of how you're able to do that. And number 4, this process is designed to be scalable, specifically scalable in volume versus surface area. So in fact, this process works more efficiently the larger reactor you go versus small reactors. So as I mentioned, MRE is you break down the metal oxides through electric current. The amount of energy you needed depends on the temperature and the atmosphere within your reactor system. On the left is the free energy of oxide formation energy requirements based on a 1600 degree Celsius temperature at 1 atmosphere. Now, for folks who have heard me speak before with LSIC, I often say that MRE is very challenging to develop, and specifically for oxygen, but it is an order of magnitude more challenging to develop the process to extract out high purity metal extraction. And that's for a few reasons. Number 1, the composite metal oxide feedstock is different on the moon no matter where you go. So we don't really know what we're putting in our reactor until we actually put it in. Unlike iron ore on Earth, where you have a pretty good idea of what you're doing, such as for molten oxide electrolysis processes. Number 2, you are dealing with very high temperatures, and in and of itself, that's not actually that challenging. But what is challenging is dealing with all the material challenges that comes with that, specifically the corrosive materials at the high temperatures we're dealing with. Number 4, when you're doing the process, there's a multivariable electrolytic composition. So the composition of electrolyte or the regolith is always changing as you break apart that oxide and then form new alloys. And number 4 is you're operating these systems autonomously on the moon. So that, of course, comes with significant challenges. Here is our current product offering. I'll kind of explain where we are in technology development on the next slide, but on the left, you'll see the constituent elements, and on the right, you'll see the slag and different alloys. We are focused on high purity. That's how we're designing our process. That's how we're designing our reactors. So as I mentioned, oxygen is a byproduct, and we're able to get, we're focused on getting 3/9 purity of oxygen. Iron, we're at 99% purity. Silicon, we're at 5/9, so 99.99%. Aluminum, 2/9, and then magnesium is also 2/9. And then in addition to that, just how the MRE process operates, we can also provide various ferrosilicon alloys, ceramic metal oxides, of course, just the plain old metal oxide slag. And then we can actually alloy different metals as well. We can put these various materials in various different final form factors. For example, the oxygen we're providing in compressed gas as part of that NASA program. We can put almost all these materials into ingots, some of these materials into wire for additive manufacturing, and powder as well for additive manufacturing, and then we can cast a lot of these materials into various structural elements. Currently, Lunar Resources is developing a major effort to commercialize molten regolith electrolysis on the moon in the near future. We are funded by the US government for developing our reactor, our demo reactor for a 2024 mission. And this reactor, it's sized to process about 150 kilograms of regolith per day, per Earth day on the moon. I know a lot of other folks are focused on a little bit smaller reactors, but one of our biggest challenges is operating these systems autonomously. And to really reduce that risk of doing that and really demonstrate the process, we felt like we would not be reducing risk unless we went bigger. So that's why that system is so big. So that mission is planned for 2024. Our pilot plant mission, we're targeting 2026 to 2027, a 1-year mission. And we hope to process about 50 metric tons of regolith on that mission. And then 2028, our goal is to be operating commercially with a target goal of 1 million kilograms or 1,000 metric tons of regolith processing per year. Carl, I apologize. I am not able to put up our actual flight hardware in these pictures. They were there, and our lawyers, of course, stripped them off. But on the lower right, sorry, on the bottom picture, you'll see one of our lab cells, extractor lab cells. And if you can look closely, you'll see some bubbles coming from the melt. That's actually oxygen coming up. That picture was taken about 2 years ago, but thought I would add that.
Hey, Elliot, just as a quick heads up, you have 30 seconds left.
30 seconds. Wow. All right. So I want to just mention this, that there are various other countries developing molten regolith electrolysis or similar systems. One country in particular, China, we believe has actually demonstrated MRE on the moon. I don't have time to obviously read through that, but read through the right, but I wanted to mention that. And last but not least, in order for us to implement MRE, we need a power grid on the moon. So, and a very large power grid. So we would ask the US government and NASA to prioritize a global electrical power grid on the moon to enable large scale resource extraction. Hopefully I'm on time.
Good enough. Yeah, thank you very much. So all questions, please put them in the Q&A session. Elliot, thank you very much. Excellent presentation. Please answer questions. You had a lot of specific questions for you in the Q&A, so jump into Q&A if you would and start answering them. And we'll get to other questions during the panel that you can't get to here. So let's move on now to our next talk. Sierra Space, Brant White will be presenting. And it looks like we have the slides up. Brant, are you up?
Yeah, Andrea should be driving this.
Looks like she is. We're good. Okay, Brant, all yours.
Okay, you can go to the next slide. So yeah, I'm Brant White with Sierra Space. Just give you a real quick overview on carbothermal for those of you who aren't aware of it. In a nutshell, it's a mature industrial process to make high purity silicon on Earth, and we've leveraged it to extract oxygen from lunar regolith. So the nice thing is it works with both the Mare and the Highland simulant, but at a very high level there, we just take the lunar regolith in, we heat it up using direct thermal energy. You react it with a carbon carrier, which is recycled in the overall process. So your net output is just oxygen gas and then your processed regolith slag. We've been developing this technology for a little over 20 years, actually, at Sierra Space and some other earlier companies. And currently where we're at with this, with one of our NASA contracts, is advancing the technology to TRL6 here in a couple of years. Next slide. All right, so as I mentioned, our primary product is gaseous oxygen. A big caveat I have to say here, I guess, is for the scope of our work through all these years, our focus has been on that oxygen. The byproducts that we create have always been considered basically waste material. So we haven't put a lot of effort or had a lot of reason to fully characterize those. So that's definitely something we would want to do going forward as you look at it as a supply towards the demand side. All our testing that we've performed has been with, almost all of it's been with JSC1 Mare simulant or the GreenSpar 250 Highland simulants. As I mentioned, we reduce with the process both the silicate minerals and ilmenite, so that allows us to use this process at any location on the moon. And then I'll go into more detail with this lower down, but the main byproducts we would get aside from the oxygen then is iron, silicon, processed regolith solid. So you can see a melt there on the right. So just kind of almost like igneous rock chunks of material that would be, low dust, but you could use them as construction materials. And then another really interesting output stream we have that is separate is silica fume is created as a byproduct in the reaction, and that's extracted out as a gaseous process stream that's condensed. So that might be a really attractive way for people to get access to silicon out of this process without having to do something like grinding up and post-processing the melts where the other reduced silicon is. And then just to note, you can see there's some little iron beads there. That's actually the Highland simulant, so there is some iron present in it. But the iron is immiscible in the greater overall melt, so it would be a little easier, I think, to separate out in post-processing. Next slide. Going a little more details here of what we currently are producing and what I would say are immediate needs to move the ball forward, looking at other products. So the material we make right now, the melted regolith, depending on how we run the process, is anywhere from 1 to 10 centimeters in diameter. You can think of it as a bead shape or as a hemispherical melt shape. I don't think it would be difficult at all really to crush that material, but we don't have a need to do that in our process. The iron containing beads, as I showed, were discrete components. If you're processing mare material, those iron beads are a much larger size relative to the overall melt. So there's some advantage, and obviously there's a lot more iron there. And then there's also some sintered, unreduced regolith that exists at the edges of the melt. If you look at the photo on the right, you can see we use the regolith as its own insulating container, so we get around the material's compatibility and corrosive issues by doing that. Where I really think near-term additional research is needed, we need to quantify what the actual structure and composition is of those byproducts that we create. So we've done some testing, but the analytical testing we have done always assumes that the materials they identify are in their common oxide state, and you'd want to do some testing to better understand what's truly there, not just the oxides you get from the testing. So are they fully reduced or partially reduced? Does the iron exist as a ferrosilicate or what? The silica fume, we've done testing on that. So by mass, that is about 80% silicon. The sodium is around 6%, and then aluminum, calcium, sulfur, and it are all down in the percent or 2 range. But that's obviously going to be dependent on your feedstock as well. One other big thing to highlight, we use concentrated solar energy to do our heating. So we bypass the efficiency losses with solar cells and using electricity. And just because of the nature of the process operating at 1600 Celsius or higher, you've got a lot of heat that's going to be radiating off of that we have to reject. So we're looking at ways to do that and utilize that, but in an integrated system, other processes could use that heat that's coming off at say 800 Celsius or so. If you size it for the kind of nominal 10 metric ton per year oxygen pilot plant, you're talking about almost 0.5 gigawatt of hours of possible heat power there for other processes. And you could just also use that direct solar processing approach, for providing your own heat in other production schemes. Next slide. So looking at a little lower hanging fruit, as much as that exists on the moon. Near term, I would say, we need ground truth. So a CLIPS mission or something to really understand how this process works using the real regolith and what quantities we're getting produced there is necessary. Solar wind gases are something that we could potentially collect as part of our processing as well. Helium-3 is probably the most attractive of those because you're talking about small quantities for any of this stuff. But until we have fusion, I'm not sure what the uses are for that. Iron, I would say, is the most likely easily available output product. So we already know we're creating a good amount of that with the mare. If you had a cislunar, refueling depot or something, that would give you a good reason to have oxygen production at the equatorial region, and then you could produce a lot of iron from that. There are some polar regions, per my understanding, that also has some iron. And then I've also seen some research that indicates if you have the ferrosilicon alloys, those can be used as an input, as a feedstock for 3D printing uses. So, and I talked about the silica fume, but I do think that's a very interesting avenue for already having kind of a partially purified, easy to get to product for silica. Next slide, please. So there's longer term things I think that would require more technology maturation. I know there are concepts out there for solar cells that can use a lower purity silicon. So our process could provide at least some feedstock for that. The silicon carbide is another potential product we can make. We would have to tailor our process conditions a little bit to make it. From our standpoint, we want to recycle that carbon and not lose it, but you would have to give some of that up in silicon carbide. So by bringing some replacement feedstock from Earth, you could make silicon carbide on the moon for the process, for the uses you need for it there. And I actually went faster than I thought. So the next slide is just a wrap up. As many companies, we're hiring and growing enormously. So if anybody wants to reach out to me, I'm happy to field questions, but otherwise you can look at our website for careers as well.
Brant, thank you very much for your presentation. You have effectively gotten us almost back on schedule. So excellent. I do want to continue to have questions answered by text in the Q&A.
Yeah,
So if you would.
I'm going to go through the Q&A and try to answer questions as I can here too.
Yeah, appreciate it. Appreciate it. I know Elliot's doing that as well. Okay. Again, thank you very much for your talk, and we're looking forward to your participation in the panel. Let's move on now to, is it Uday? Who from Airbus is giving the presentation? I have two names. I thought Uday was. Are you there? Uday, it is. I can't hear you if you're speaking.
Yeah, I'm going to start, and then Achim is going to continue with the rest of the presentation from Airbus.
Fantastic. We hear you well. We'll leave you to it.
Good afternoon, everyone. I'm Uday Pal from Boston University, and thank you for inviting us to participate in this workshop. So I will be summarizing our work on solid oxide membrane-based anodes for metal oxide electrolysis in molten salts. My collaborators, students, postdocs, and sponsors are all acknowledged in this slide. I've not included Airbus and other European collaborators here, which Dr. Seidel will do in his presentation a little later. Next slide, please. Here is a schematic of the electrolytic device. The heart of the device is the oxygen ion conducting solid oxide membrane. One side of the membrane, you can see at the top, is the oxygen producing anode, and the other side of the membrane is exposed to molten halide flux or salt containing the metal oxide. The cathode is placed inside the molten halide salt, and then an electric potential is applied between the anode and the cathode. And when this potential exceeds the dissociation potential of the metal oxide in the halide salt, the metal is reduced at the cathode, and the oxygen ions in the salt migrate through the oxygen ion conducting membrane to the anode, where they're oxidized to oxygen gas. So the key advantages are listed. It is a one-unit operation, less energy intensive, operating at very high Faraday efficiencies in high 90s, less capital intensive since it is modular and can be scaled easily, has no carbon emissions while producing metal and oxygen, and simple to operate since the only consumable is metal oxide. And the operating temperature is, depending on the salt, it is between 800 to 1100 degrees centigrade. The property requirements for the molten halide salt electrolyte are listed. It needs to have low electronic conductivity, so larger potentials can be applied without destabilizing the membrane. High ionic conductivity to reduce cell resistance, low viscosity for faster transport, low volatility for compositional stability, and chemical stability in contact with the membrane for long-term operations. Key innovations include anode design and assembly, and engineering the molten salt electrolyte to have all the required properties. Next slide, please. We have employed this electrolytic cell to demonstrate the feasibility of producing many technologically important metals as listed here: lithium, magnesium, calcium, titanium, tantalum, iron, copper, aluminum, silicon, and also some of the rare earths. And many of these metals are present in lunar regolith. Others have also used this technology to produce alloys. So this is a proven technology. Next slide, please. One variation of this technology I'm working with Airbus is their patent pending Roxy process, regolith to oxygen and metal conversion. It uses the oxygen ion conducting stabilized zirconia-based anode structures to collect pure oxygen while reducing the regolith in porous metal cathode cup immersed in the molten halide salt electrolyte. Next slide, please. Some of the salient features of the Roxy technology are listed here. The schematic is shown on the right. The anode is based on the oxygen ion pump design that was developed by Airbus for the International Space Station. It produces high purity oxygen. The unit is small, compact, efficient, low mass metal and oxygen production capability for the moon and beyond. Compared to other processes, it is universal, powder-based, and has a high current efficiency. With this technology, one can control the reaction rate, selectively reduce metals based on the potential applied and upstream beneficiation, and to further develop this technology for lunar applications such as converting regoliths to usable metals. We would like to explore maybe NASA's Luster program as a possible source of funding for future. So with this, I'm going to request Dr. Seidel to continue with the rest of the presentation. Next slide, please.
Can you hear me?
Yeah.
Okay, so good afternoon, everybody. My name is Achim Seidel from Airbus, and I will continue this presentation. So we are working on this topic on two levels. One is called Roxy, regolith to oxygen and metals conversion, and the other one is MEFAM, the metals factory on the moon. Next slide, please. So here, a quick overview. I mean, Uday has already presented Roxy. So it is a molten salt electrolysis process. You can see the schematic on the right-hand side. With that, we can extract metals, alloys, and high purity oxygen from regolith. And we see this as a central part of the metal product value chain on the moon. This value chain is shown at the bottom right. So it includes all the steps from mining all the way to additive manufacturing to produce finished products. And that leads us to the other topic, MEFAM, the metals factory on the moon. This covers the end-to-end value chain from raw regolith to metal products and includes several processes and technologies from mining to additive manufacturing. This work is done in a large international team, including Boston University, Airbus, and many others, including the best that the German research landscape has to offer, such as Fraunhofer, the world's leading applied research organization with 76 institutes and research units and over 30,000 employees. Next slide, please. Okay, so here's some information on where we are with Roxy. So we have demonstrated the process in the lab. We have reduced regolith, produced high purity oxygen. We could reduce the process temperature to 850 degrees. We could show that we have a very high current efficiency and can operate at relatively high cell voltages. There's some pictures on the right showing some elements of the process like anodes, cathodes, the salt, a reactor and things like that. In addition to the work in the lab, we also have a range of products under development. The first one that I'm showing here is a Roxy Lab Demonstrator. What's special about this is that the reactor is placed in an external vacuum chamber. So the process takes place under simulated lunar conditions and allows us to study the process under those conditions. The next one, number two, is a lunar demonstration model to produce 50 to 100 grams of oxygen in one lunar day. In addition to that, we have developed what we call mini Roxy. The idea here is that it may be interesting to also be able to demonstrate the process on a very small scale in a situation where the resources that are available for such a reactor are very small. So the idea is to develop something that would fit even on a rover. And last but not least, we are also looking at scaled up versions, pilots, plants, and things like that. And we have found that as we increase the size of the reactor, the energy efficiency actually increases and is getting better. Next slide, please. Now, a few words about MEFAM, the metals factory on the moon. As I said, this covers the entire metal product value range from regolith to the metal product. It's a top-down, end-to-end approach covering various technologies. So what you see in the chart is the materials that we get as the result of the process steps one by one, and the process steps in blue, and the final output of the sequence, the products that we are producing in green. So the process steps, they start with excavation and transportation, followed by beneficiation, reduction, extraction, and refinement, and then manufacturing on the moon and in deep space. Next one, please. The main ideas and approach here for MEFAM is we are starting with the viability criteria as driver for technology selection. So we consider that it is absolutely needed to minimize transportation costs for the hardware. This also includes the minimization of the need for consumables, the use of near waste-free processes, because otherwise the transportation costs become prohibitively high. And this drives the assessment of technical and economic feasibility of candidate technologies. So on the technical side, we have already identified some methods of choice for some of those technologies and process steps, but we are also looking at alternatives. So for reduction, we favor electrolysis and additive manufacturing, obviously for manufacturing tasks. We further consider that...
I'm sorry to interrupt. I just wanted to let you know you've got 30 seconds left.
Okay. So then let me move on to the next slide. Okay, outlook and next steps. So here you see a sample of reduced metal that we have produced with Roxy. So obviously MEFAM is a wide field. We need to work together in a multidisciplinary approach. We are aware of the fact that we may not address all the suitable and promising technologies, so we are open for cooperation all along the process chain. And the next steps in the lab are obviously metal production and post-processing for Roxy and for MEFAM to try out manufacturing processes and applications. We were asked to comment on potential roles for NASA as we see it, so we believe it will be beneficial if NASA could act as an enabler of cooperation on end-to-end process chain implementation, support sharing of concepts, experience, and samples, support process technology developments, and provide funding for future development steps. Thank you.
Okay, Achim, Uday, thank you very much for two excellent presentations and staying on time. The next presentation is by Pioneer Astronautics. Mark Berggren, are you available?
I am here.
Fantastic, Mark. Have
Okay.
at it.
Thanks. Well, I'm glad to be here today to talk about work here at Pioneer Astronautics regarding iron and steel production from lunar regolith using hydrogen reduction. Next slide, please. A lot of what I'm going to talk about is based on work we're conducting under NASA SBIR Phase 2 sequential contract titled Moon to Mars Oxygen and Steel Technology with our partners at Colorado School of Mines and Honeybee. Next. So what we've done is to set a baseline process by linking together a number of unit operations that we felt that would allow us to go from start to finish, from regolith to rebar, using techniques that either have heritage or demonstrated technologies that can give us what we feel is the best chance of making it without relying on a miracle to happen at some point along the way. And so just briefly, what those operations are initially would be to beneficiate lunar regolith to boost the iron oxide concentration, whether that's from ilmenite in rich form in mare soils, relatively speaking, or even in highlands type soils, or with some prospecting and care and attention, finding those anomalous high FeO regions near the South Pole, closer to Artemis operations. We would, and by the way, the photos show kind of from top to bottom there some of those methods. So the beneficiation would be particle size separations, magnetic and electrostatic separations. We would then go to iron oxide reduction on the concentrated regolith using hydrogen reduction in an automated apparatus with some durability and hopefully long-lived hardware. The residue then from reduction would advance to a melt refining step where we bring the material up to a temperature that allows the metallic iron to coalesce and separate for recovery, then leaving us with an oxide byproduct. The iron would then be alloyed as required to meet the needs. That would then be poured into rods, which would be drawn into wire. And then we would employ a wire-fed, arc-based additive manufacturing method to produce components. The lower photos there show some work at mines prototyping this method with an electric arc method with a low alloy iron wire, with the product there shown as an iron sheet. Next slide. So our overall approach for this during the MMOS program and then looking over the horizon to what happens next is that we want to identify what the minimum processing requirements are to be able to produce a wire and example components that could be useful for supporting human habitation on the moon. With this minimum processing, then we would establish what are the basic performance characteristics, technically speaking, in terms of strength and ductility and that sort of thing. That would allow us then to identify what sort of alloying agents are required to meet the actual performance specifications and technical requirements. That would be done in conjunction with trying to identify what the sources of those alloying agents might be, whether it's ISRU, recovery from scrap, or earth-supplied materials. These things would have some impact on the lunar steel production leverage, process leverage, and the costs. But altogether, these things we feel would help then to lay the foundation for establishing lunar manufacturing standards. Next. So commenting on the hydrogen reduction process itself and the effects on the recovered metal, it's interesting to note that because of the fairly low reducing power of hydrogen compared to others in carbothermal reduction or in with electrolysis, so that reduces our oxygen yield. But at the same time, because of that reduced reduction power, we can only reduce things like copper, nickel, cobalt, and iron oxides that are present in the lunar regolith. But it's really only iron that's there in significant quantities, the result being that we get a relatively pure iron product directly after separation from the oxide slag. We do get some impurities, and based on working with simulants, we see primarily things like sulfur and phosphorus that can report to the metal. Typically, we've seen things of less than 0.1 or 0.15%, but these can contribute to some potential deterioration of properties, but there are conventional and with vacuum processing, even alternative ways to deal with that. Next. So in producing metal to be used in a useful fashion, we have to consider what sorts of factors are relevant. Certainly strength, ductility, hardness, that sort of thing. There may be applications where thermal expansion, conductivity, heat capacity, electrical conductivity all have something to do with it. And perhaps importantly, minimum maximum use temperatures, where on the moon at the equator, we might have from -150 to +100 C, but as low as 25 K in shadowed regions. Next. So in looking at alloys, these are used to boost the strength, ductility, workability, and corrosion oxidation resistance In mild steels, these are generally added at pretty low concentrations, less than 1 to 2%. Terrestrially, often these would include carbon and manganese in some combination, but other agents can be added as needed for hardness and other properties. Heat treating is going to be performed to alter the grain structure to give us the mechanical properties we need with those alloying agents present. Next. And it's worth, I think, pointing out some of the potential advantages of operating in vacuum. In melting, for instance, in vacuum, we can release volatiles, dissolved gaseous compounds, and this can also help to minimize voids and reduces the need to supply the kind of conventional additives that would be done in a blast furnace or steel making that would be consumables. Heat treating in vacuum can really help us to minimize issues with scaling as we're working with materials. Typically, if we're, say, drawing wire in air, we get some scaling that needs to be removed mechanically, or more typically by pickling chemically. A lot of that's eliminated by operating in vacuum. Thermal vacuum operations can also give us an opportunity to join metals that might otherwise be difficult methods or impossible to use under an air atmosphere. For instance, we might be able to eliminate flux for welding and allow us to braze under certain circumstances as well. And these types of methods, vacuum induction, melting, and heat treating, are terrestrially used at this point, kind of as specialty treatments for both iron-based and light metal alloys. Next. As one quick example of where we might need to make some changes in order to meet the usage requirements, we need to look at these low temperatures. Typically on Earth, metal standards are such that under normal atmospheric conditions, say -45°C, everything's got to hold up, but we get into a special region when we start getting colder than that. Under the steel category there, and looking at the thermometer on the left, as we start getting colder, one thing we can see is that we go from, say, -100°C, where we might need 3.5% nickel. That increases to 5% as we approach 150, and 9% as we hit -200, and potentially even more for even colder regions. But what this says is there's a solution. It helps us to define what direction we might need to go, and what the impact of those kinds of things would be on the process and its leverage and economics. Next. So really, to summarize, our approach here is to try to establish and demonstrate the minimum requirements on each of these steps for metal production from regolith. As technologies advance, we can apply process modifications that can help boost our yields, our throughputs, and the quality, while trying to reduce energy and power requirements. And as further advances take place, then we can look at modifying or even substituting process unit operations and again, continue the goal of boosting yields and reducing power and mass requirements. And altogether, I think these things can lead toward a robust lunar manufacturing environment. Finally, I'd just like to acknowledge project teams working on the project. Aaron Paz in particular, our technical monitor at JSC, the whole NASA SBIR program, and of course the Lunar Surface Innovation Consortium. So thank you very much.
Brant, thank you for the presentation and staying on time. Very interesting. So there've been a lot of questions for you in the Q&A session, so if you would please log on. I remind the other panelists, please do that as well, and you'll get a chance to answer questions live. Well, not exactly live. I'll try to rephrase them and ask them like we did in the last panel. But
Very
anyway,
good. Thank you.
Thank you. We're moving on now to Geo. Are you ready to speak?
Yes, I'm here. Can you guys hear me okay?
Loud and clear.
All right. Awesome. Well, good morning, everybody. My name is Geo Licciardello. I'm with Terraxis. I'm joined today by my colleague, Andreas Joachim, and we are based out of Broomfield, Colorado. To any of you guys who are in previous workshops working on oxygen generation, these slides might seem pretty familiar, but since it's a different focus here today, we're still going to go over our reactor operation and then what sort of metallic products we can produce. So what we are working on is what we call the Vapor. It is a vacuum pyrolysis reactor for transforming raw lunar regolith and disassociating it into different constituent products. Picture here on the right-hand side is our reactor prototype that we have here operating in Broomfield at our lab. And we'll be going through how it all works. So next slide, please. So this chart here shows at a pressure of 100 pascals, what component metal oxides present within regolith disassociate as you increase temperature. One of the big advantages of this process is it's a very high temperature process. So we actually operate in sort of the above 2000 C regime, unlike some of the other processes that use different techniques that operate at much lower temperatures. It's kind of a brute force approach where once you get above certain critical temperatures, you begin to evolve all these different products. So you can see the chart here. You start with these different metal oxides, silicon dioxide being the most prevalent in lunar regolith. Then once you get just under 2000 C at this particular pressure, these different metal oxides disassociate into, well, different oxygen compounds, but also different elemental metallic compounds like iron, magnesium, aluminum, etc. So our focus was originally with this to be working on it as an oxygen generation tool. However, all these other products get generated as a matter of course, because in order to get the oxygen out, we're already surpassing the temperatures where we get these other compounds out as well. So we're working with raw regolith and not a specific mineral compound of regolith or lunar ice deposits. We really just sort of take the sand, heat up the sand, and all sorts of stuff starts to come out of the sand. So next slide, please. So this slide here sort of shows where our reactor would sit within a greater ecological, network of ISRU systems on the moon. The reactor element that you see in the photograph, that's really what we focus on today. But we are going to need help with other partners and other stakeholders in the ISRU ecosystem with the other upstream and downstream processes. So excavating raw regolith, delivering it to the reactor, that's going to be composed of a whole bunch of kind of raw minerals that need to be cracked and separated, which happens in the reactor. Different elements will begin to condense out at different temperatures at the pressures that we operate at. And then those would have to get either disposed of if they're just waste products that no one has any need for, or separated, stored, and processed for whatever end uses they may be, whether it's a construction material or as a propellant or as a breathing gas in the case of oxygen. And then, of course, we need power. We're relatively agnostic to where the power comes from. However, we do run our current prototype essentially with a solar power simulator power supply. So we're assuming that that would probably be, at least in the near term, the most likely power source available to us. And then, of course, there's benefaction, O2 storage, and bringing that wherever it needs to go, as well as all the different metal compounds that we get out of it. So next slide. So here's a simple kind of functional breakdown of how our reactor works. At the heart of the reactor, we have a high temperature crucible, which regolith is deposited into. That crucible sits within a reaction chamber, which is maintained at a, I would say, mild vacuum. We're talking around 100 Pascal range, maybe a little bit lower or higher, depending on what you're specifically doing. We receive power from a power source, which in our case, in our lab, is a simulated PV power supply, which then goes into our proprietary drive control electronics, which then drive a series of electromagnetic coils. Those coils wirelessly input power to the crucible directly, which then reaches the critical temperatures we need to begin disassociating the regolith. As the regolith is heated up to these critical temperatures and disassociates, those products released as vapor will then move out of the reaction chamber into a condenser assembly, where depending on the temperature in the condenser, different compounds will begin to condense back out from vapor phase back to other phases. We have a pretty simple liquid cooling loop that we use here on the ground to maintain the unit at temperature. And because we're not on the moon, we don't have a natural vacuum to work with. We have to use a traditional vacuum pump. But fundamentally, it's a way of wirelessly transmitting power relatively efficiently into a high temperature chamber, where then the regolith can get up to the critical temperatures that are needed to really just sort of brute force break things apart without any additional chemical processes or different chemical feedstocks needed to do a specific reaction. This is purely a thermal reaction, really. So next slide. So Andrea, I think if there should be a little button you could, or whoever's driving, to run the video for people, just so you guys can see what this looks like. But
which video are you speaking of?
Oh, it was that image right there was a video, and okay, well, maybe it got, oh, there we go, perfect. Yeah, so this is a video of our prototype running a couple months ago. You can see the crucible is glowing white hot in the center of that chamber. And that chamber is being maintained at a reduced pressure. Not hard vacuum, but a decent vacuum. And the way we measure temperature, because it's a very, very high temperature process, is actually optically. So we have an optical temperature probe that will measure essentially the black body radiation output of the crucible and then give us a readout. So we operate above 2000 C. We've operated for varying lengths of time, from a couple of minutes up to about an hour steady state. And our focus to date has really been on the core sort of power delivery energy management system, to make sure that we can sustain and hit these critical temperatures needed to separate out the different materials. So the test stand has been going through a lot of different configuration changes, but yeah, the core value proposition of hitting these temperatures has already been demonstrated. So next slide. Excuse me. So what do we generate? So unlike some other processes which are focused on a very specific kind of output, we're going to end up, just as a matter of course of operating at the temperatures and pressures that we are aiming for oxygen generation, to end up with these resultant yields. So the primary non-oxygen product that we would receive is actually silicon monoxide, which I am interested in learning from the demand side guys talking later today, if there's any particular interest in silicon monoxide. I think we see it a bit more as a slag, byproduct that is less useful than some of the other products, where the next most prevalent would be elemental iron, which could be used in all sorts of applications, as well as elemental aluminum, elemental magnesium, calcium, and then a tiny bit of titanium and other small trace products which aren't listed. Now, how exactly those get separated and benefacted for end users, I think depends a lot on what those end users want. And that's what we're really interested in learning here today, is talking about, do you guys want, should we just focus on giving you some iron rods and you'll have fun with that? Or do we want to try to combine some of these components together and alloy them as part of a secondary process? Or just hand you your container of different products and then you go to work. So the beauty is that essentially purely by varying our pressures and our temperatures, we can optimize for extracting any one of these in particular. But in a general sense, this is the amount of yields that we would get, per ton of regolith delivered to our door. You would get about 100 kilograms of iron out the other end. So next slide. So as I mentioned before, our focus really up till now has been a lot on the reactor power system and improving our power efficiencies, being able to run at higher temperatures for longer periods of time. But as we refine that and then look ahead to the condensing and separation aspect, that's where we really need a lot of feedback from other stakeholders here, because you are our potential customers and partners on using the products that we generate. So we think a temperature gradient approach for separating out the products is likely the most elegant and easy to implement solution. But how effective is that going to be? And do our customers need really precise, ultra pure elemental iron, for example? Or is it okay if it's mostly elemental iron, but there's some other, processes that condensed out that are captured with it? I'm sorry?
Sorry to interrupt. You have 30 seconds left.
Okay, thank you so much. What form factor do you want? I know that rods and wire and powder are common form factors. Depending, we could be able to generate any one of those, though powder is probably going to be the most likely output that we would be able to get easily. And are there other novel uses for products like silicon monoxide, which we're going to end up with quite a bit of? And also, where do we want to draw the dotted line between our active system that's generating these products and then downstream processes where maybe additional alloying, additional purification, other form factor modification takes place to make your actual final end product? So I'm very happy to present this to you today. Thank you so much for your time, and I appreciate the opportunity.
Geo, thank you very much. Very interesting presentation, and some of us enjoyed the video, so nice to see it in operation. Okay, so we are going to move on now to our final presentation. It's going to be a video, actually, essentially very same thing. And after the video, we'll move on to our mini panel. So again, if you have questions for any of the speakers, including the one that's presenting the video, Antoine, out of Kilncore, please put those questions into the Q&A session. All right. So Andrea, I know we have the video in the folder. All right, fantastic.
Hello, everyone. Today, we are presenting the latest concept from Kilncore, a company first introduced in June 2021. Last December, Carl asked us what the low-hanging fruit for metal production on the moon was. Our answer, bearing in mind a lot of it is still early research, comes in two parts. The first part is Kilncore Volcano, the metal addition. Kilncore Volcano was designed as a prototype pilot plant for oxygen production from regolith, using molten regolith electrolysis. The process combines several patent-pending innovations to support a continuous flow model where key parts stay in a steady state, avoiding thermal cycles. The reaction cell generates gas, which is continuously removed to keep a steady, selected chamber pressure, pushing the molten residue through the bottom. A continuous mass flow of regolith is added to what we usually call the hot end from a series of reservoirs that can be pressurized and depressurized in a cycle, allowing constant non-stop transformation. That initial prototype is under active development, with regular iterations to achieve the first seed, slag-emitting electro device. The version we are currently testing is not optimized for metal production, but for other considerations. It is, however, a great basis for one. Since before the company was founded in 2019, we had planned to use multiple ways to control the flow of molten recycled glass, such as having different temperature levels in the hot end, using sounds and ultrasounds to change behavior of the molten material, or using the weight of the molten material itself. In 2020, we added using a pressure differential and electrolysis, and started focusing on lunar regolith. All these methods combined provide some unique properties that can be leveraged for metal production. In particular, The electrolysis, of course. The pressure differential to push the slag, and having 2 temperature levels for slag purification purposes. The geometry and other parameters are adjusted for maximal metal production rather than efficiency. We expect sophisticated clients will want pure metal and not just slag, so the seed output must be purified. A typical method is the use of ceramic filters. These can remove all sorts of impurities depending on their specifications. They also require pressure for the molten metal to go through, which we can provide, since that is already included in the prototype as one of the flow control methods. The pressure will simply be higher when filtering. The mass flow for a given pressure will provide indication of the molten metal filter being used up, thus requiring change. Highland regolith has a large amount of aluminum and silicon, so the slag from the molten regolith electrolysis will contain both, under ideal circumstances. While the electrolysis temperature needs to be high, the output temperature can be kept lower, at a level where aluminum is liquid, yet silicon solidifies in such a way it can be mostly filtered. The output of that stage could be considered an exotic alloy of aluminum that could be shaped according to the client needs, such as wire or powder, using more traditional methods. The spent ceramic filters will be full of oxides and silicon, but we can be clever and make them hexagons for easy tiling in applications such as heat-shielding tiles, landing pad tiles, road tiles, construction bricks, and more. Thus, the spent filters have great value. Note, the silicon in the filter could be partly recovered by reheating the filter in a centrifuge. If the original slag contains mostly silicon and little aluminum, it should be operated at a higher temperature to let the silicon pass while still filtering oxides, and the output would be mostly silicon, which is also useful. To make that work, it is necessary to have an unending source of ceramic filters. That is where the second part to our answer comes into action. The following is currently an early concept stage, so please keep an open mind. We propose to manufacture the ceramic filters using only lunar regolith and the exotic aluminum alloy produced by the system itself, using earth filters to initiate the loop. In 2017, we bought our first kiln and several tons of recycled glass for experimentation. We did many tests over several months, one of which was the partial fusing of glass granules. The result is solid, yet lets pass gases and liquids through. This was not considered important at the time, but was still documented. In the context of ceramic filters, and considering regolith instead of recycled glass, it becomes the foundation of an idea. We proposed the partial fusion of lunar regolith, mixed with a bit of metal powder, in a reduced gravity environment to mass manufacture hexagonal molten metal ceramic filters. Lunar regolith is highly porous, is very angular, can hook to itself, and is thus partly self-supporting. Loose regolith is therefore full of voids, but not by itself able to support slag being pushed through it without being destroyed. To transform it into a usable ceramic filter requires at least partially fusing it and having some control over the final characteristics. Using an appropriate hexagonal mold and a variant of the high-temperature, high-pressure cooker, such as our other product, Kilncore Fusion, ceramic filters could be mass-produced using only locally produced lunar materials, that is, the raw regolith and the metal post-filtering. The reduced gravity of the lunar environment should make this easier than Earth's gravity, but considering the Artemis roadmap, we propose finalizing the research and development of this approach on the Lunar Gateway, bringing us to LGMM CFPP, the Lunar Gateway Molten Metal Ceramic Filter Pilot Plant. We would be happy to collaborate with a U.S. partner for the development of a small proof-of-concept unit to be installed and tested at the Lunar Gateway, making it even more useful for the future lunar economy. Regardless of the method that ends up being used, anyone wanting pure metal could benefit from locally produced ceramic filters. Provided an anchor client, which would facilitate financing, this could be ready for the start of the Lunar Gateway operation. Once mastered in the absence of gravity, the process could then be adapted to the lunar surface. It is expected that ceramic filters made in the presence of gravity could be less performant than in its absence, perhaps significantly so. In that case, they could still be used as pre-filters. With that, we can summarize the proposed Kilncore approach for metal production like this. The raw regolith is deposited in the currently depressurized reservoir. The reservoirs pressurize and depressurize in cycles. Regolith in the pressurized reservoir is fed to the reaction chamber, where high-temperature molten regolith electrolysis is done, Using an appropriately high column and a lower temperature section, which will crystallize the silicon while leaving the aluminum liquid, the slag is pushed through a pre-filter, which will clog more often, but is easier to produce. Then the higher performance filter, before being shaped into wire or powder using traditional methods of the industry. The discarded filters are used as heat-resistant tiles. A few weeks after being asked about the low-hanging fruit in metal production, this is the concept we were able to come up with. As this workshop is all about matching supply and demand, assuming the demand is vigorous and the funding plentiful, a fast iterative approach would allow the Lunar Gateway Molten Metal Ceramic Filter Pilot Plant and the Kilncore Volcano Metal Addition Pilot Plant to be validated in relevant environments by the end of the 2020s. The metal production pilot plant is designed to operate using between 40 kilowatts and 50 kilowatts, ideally nonstop. A production rate of a minimum 1 metric ton of metal per month would be the target. This would require several tons of ceramic filters, producing several tons of tiles. The Lunar Gateway pilot plant would use about 10 kilowatts when cooking the filters. Since this is planned to be a relatively compact unit, the lunar surface variant could be integrated directly in the same container as the metal production plant. Some of the companies on the demand side of metal in this workshop have 3D printing capabilities for large objects. Such large objects could be radiators for thermal management, since those will be needed. They could also produce many of the parts of the proposed pilot plants. It would be advantageous to have as many as such 3D printed parts to take advantage of the exponential effect of self-replication. Only a fraction of the weight of the pilot plants would then need to be sent to duplicate them, most notably the electronics and the interchangeable reaction cells that will inevitably be consumed. This is true regardless of the approach used for metal production. Once 3D printing metal on the moon is possible, being designed with parts producible on the moon is best. A lot of man-made things will be transported to the lunar surface over the next decades. It is important to remember that not only machines will operate there, but mindsets too. A diverse set of companies make for a more resilient ecosystem, especially in its infancy, in a new context. With that in mind, we would be happy to collaborate with international partners on this early-stage design concept. A ceramic filter pilot plant would benefit the whole future metal industry on the moon. Kilncore looks forward to contributing to a vibrant lunar economy in a way that maximizes returns for everyone. Imagine looking to the new moon in 2064, and instead of a dark circle against the night sky, you see a small web of city lights, something that has never happened before, in millennia. This is the future that I believe we are currently building. Let's build a vineyard on the moon. Wine is made from the blood of rocks and human ingenuity, just like the exotic alloy we propose supplying. Thank you.
All right. Thank you very much. Antoine, there you are. Very nice
Thanks,
video.
Thank you.
Very good. Very good. You have a lot of questions, or quite a few questions there in the Q&A session. Perhaps
Yeah, I'm
you
gonna
can-
look into it.
Yes, go ahead and see if you can answer those questions online. And in the meantime, well, we're right on schedule. We're going to move on into our panel, which is I will be asking questions of each of the speakers, because you're the effective panelists, based off the questions in there, and hitting in many of the questions I can. But I want to lead off with one question I've been cogitating. We actually came up with a few questions before the talks, but I've noticed that, if I may take my prerogative and ask, I've noticed that all the presentations are, of course, lower TRL-ish, TRL 4, well, maybe 6, but maybe lower than 4. So it seems to be a great time in which to obtain guidance from the users, and we'll get to this in the combined session, on where to go with your technologies, right? But it's also a great time to potentially tell NASA or whoever your funding agencies are, what are the one or two things that, other than giving you $1 billion, right? Other than giving you a whole lot of money, what is the one thing that they can do to enable you? Now, Elliot Carroll has already done this. So Elliot, I'm going to skip you, because you said the one thing that's needed for MRE is a lunar power grid, so you can have a global capability there. Well, I'm going to pose the same question then to each of the panelists one after another. Start with Brant, and then Achim, Uday, Mark, Geo, and Antoine, just going in the same order that you all spoke. What is the one thing that would really enable you to build your technology? What's the one big roadblock that someone can solve for you, particularly NASA or somebody else? So Elliot, you already spoke. Brant, are you online? And this is where you guys can speak up. Don't answer by text, but actually speak up. So sharing your video would be great.
I'm online and then hear the question. I'm trying to think, we historically, we obviously our process needs a lot of power. I think everybody's does. It's melting the regolith. So we've sidestepped that some with using the direct solar concentrated energy route, and that's actually handled through a separate company that we interface with via NASA. And that helps a ton with efficiencies, but it has brought its own set of challenges because now we're having to pipe concentrated solar light in through optics that are then in a dusty regolith environment. Historically, that's been one of our challenges in terms of how to keep that all working well, but that's something that we've actually made a lot of progress on. And I think that's a technical risk that we've gone a long ways towards putting to bed so far. So if you asked me 5 years ago, I would have said that was our biggest technical challenge. Now I don't know that it is. So I'm trying to think of what the next.
Could there be any
is.
infrastructural needs or programmatic needs? I'll make this up. Like NASA saying we want to focus on building a tower, so we need, let them say we need rods. We want you to make material for rods. I mean, is that important to you? I don't, making this up, anything, any kind of direction that would help you make decisions for business.
Yeah. I mean, I suppose if NASA says they don't want, if they don't want the oxygen or they want a second product as our primary output, that would definitely drive the decisions we make. If we know we're going to be wanting to make a lot of iron in addition to the oxygen, then that we're going to tailor our process around that.
Okay, awesome. Thanks. And sorry to put you on the spot for that, but I mean, it is a panel, so.
It's okay, yeah.
Yeah, fantastic. All right. So Achim, Uday, similar question to you. If you could ask for anything other than $1 billion, that what would really help you guys get going so you could make fast progress.
Yeah. Achim, I would first defer the question to you since you are from the industry, and I think so. Are you able to hear me, Achim?
I don't hear anything.
Yeah, I don't either. I'm not sure.
Why don't we come back to you then?
No, I think he's on.
I hear him. I just
Achim,
got a note that. Oh, Achim, can you?
I see Achim, but I don't hear Achim.
I think he might have lost his audio.
Right. And so, we're not in a great rush. So why don't we just come on back to you guys in a few minutes, and Achim will get us things. And Mark, you're next in line. We'll give you an opportunity to address that.
Sure. Well, for me, I don't know if it's, maybe I'll change the question just a little bit.
Sure.
Maybe not so much enabling, but for implementation, I think that some good prospecting in the regions of interest for, in our case, looking for high iron oxide containing soils. And in addition to, say, bulk composition, some mineralogical information would be great to help define the requirements for the beneficiation step and providing a good mining plan that would give us feed over the lifetime of a plant located in a region of interest. That, and I would also add, I think, guidance on specifications ties in to this as well.
Thanks. You can use it, is what you can use.
Yes, sir.
About the moon and needs. Awesome. Thank you. Geo.
First anchor tenant going to be? I think NASA is sort of the going assumption there, as NASA does want to establish a presence on the moon. So at what dates, what products do they need the most of? Like if human beings aren't going to be there right away, do we need to focus on producing lots of raw aluminum to be used as a building material? And what price would NASA be willing to pay per kilogram of aluminum that comes out of our process? And also on the input side, if NASA is building a power plant on the moon, whether it's solar or some other form, what would the cost of electricity be that we have to pay to get that? So we can put together kind of not just optimize the technology for the processes that are most needed most early, but also put together a business case saying, hey, this is how the company is going to be successful, and have it not just be science experiments for the next 40, 50 years. So I'd say that's the biggest thing we could use from NASA is understanding kind of what price are you looking for goods, and what prices do we have to pay to generate those goods for you.
Geo, thank you. And you may get the answer not from NASA. You might get it from other industry providers.
Sure. Yeah. I mean, I don't care. It doesn't have to be NASA, but whoever is going to want the stuff that we make, we'd love to hear from you.
Fantastic. Okay. Achim, are you, I see you're muted. Are you able to unmute?
Yeah, I'm back.
Yes, I can hear you. So we were asking, did you catch the question I was posing to each of the panelists?
Say again?
I asked each of the panelists, given the state of your technology it is today, what would the one thing or things be, whether it's infrastructural support, programmatic support, or information of some type? We've had all three answers so far. What, other than money, what would be the one thing you'd need or be most useful for you to make really a lot of progress right now?
On process level, which is the molten salt electrolysis, but this is only one step in the entire process chain. So I think if we really want to make process towards producing valuable metal products on the moon, then we need to do this in an integrated approach. And this is what I've presented on Nephan, the metal factory on the moon. I think we need to work together along the process chain and really find out what, let's say, what each process step can contribute, where there are synergies in order to get, let's say, answers and solutions for different use cases.
That's very interesting question. So let me answer. Okay, processing chain. We have a breakout set group in the ISRU focus group. We call it the value networking chain. So it sounds like you're asking for and what the Geo alluded to, what is the whole model process chain system level solution to ISRU? Like what are your products in, your product out, the customer, all of your logistical support, all that needs to be defined for you. It sounds like, is that what you're saying? I'm trying to interpret your question. Interpret your answer. I think that's what you were saying.
Yes.
And okay. And that will feed, you should participate potentially in the ISRU focus group discussions related area. All right, that was an excellent answer. And Antoine.
Can I add another bit to it?
Sure, yeah, of course.
So the other thing is that the resources on the moon are certainly much more limited than what we have here, and it's so difficult to get there, right? So the thing that we really need to be also concerned about is the entire life cycle assessment, like what are the input and output from materials production to manufacturing to transportation to use, and then the end of life. So reusing, remanufacture, disposal, or combustion for energy use. The whole thing has to be integrated in such a way that we promote sustainability. And that is a very, very challenging task, in my opinion. And we should probably start thinking about it.
Maybe with this is a genesis for another workshop off the top of my head. Okay, thank you. All right, Antoine, are you online still?
Yes, I'm here. So there's 4 things that NASA could do to help me, even though I'm not in the US. I can't apply for the funding opportunities, but a letter of support would greatly help me get funding. Also, having access to test facilities would be great. That would be really useful. The other thing is the lunar simulant that we have do not reproduce the mechanical properties for like flowability that I would need to have something to test the regolith valves that we're working on. And the final thing is for everyone wanting to do metal extraction is to please bring a lot of power on the moon. So that would be very useful to get a sustained presence there.
Thank you very much. So test facilities, this is something NASA does have and it's potentially available. One can even write proposals to them to do it. One is open, in fact, ACO. Simulants availabilities, yes, there are certainly at least 2 or 3 simulant providers out I know in the US. In case you're not aware of them, you have Outward Technologies. Gosh, I hope I got that one right. Vince, anyway, and Exolith. Yeah.
I do have the 2 simulants from Elliot, but they're great for the chemical properties, but for the mechanical properties, Yeah.
So you should look on the LSIC website. We have a simulant
list
portal. And maybe that's of use to you. Okay, fantastic. All right, so we have approximately 15 more minutes on this one. We have some more questions for each of you, which I'll probably go through. Now, there's a lot of questions online, and it's really something you all need to follow up individually, because these questions, again, were mostly written to you individually, right? And I'm going to be asking questions, I think, which is to the entire group. So it'll be slightly different, okay? So for each of you, and I'll start with you, Antoine, and each of you have touched upon this to some extent, but it's kind of interesting. To what extent is there a trade between optimizing for lunar oxygen production versus metal production? And you touched upon this in your presentation, as did others. And related to that, then, again, do you need to know which metals, and you already touched upon this, what would it help for you to make the decision on how to optimize your technology for metal production or oxygen production?
So the initial design was optimized for oxygen extraction because, the first few % of oxygen to be removed is easier to remove than the last few %.
Mm-hmm.
So the idea was to get those most efficient amount of oxygen first. But for the metal edition, we want to remove as much oxygen as possible. So it's less efficient, but if there's a demand for the metal, then, and the price is right, it's worth doing that like this.
Okay, thank you. I'm going to ask the same question on down the panel, and I was mistaken when I said we have until 2 o'clock. That's when the next panel kicks off. We actually have a break in 5 minutes, but I think that's perfect for each of the other panelists to address the optimization question. And the Terraxis, Geo, you already spoke to this a little bit. Anything more you want to say on that?
Oh, sorry, Carl, could you repeat the question for me, please?
Well, it's related to optimization, right? Yeah, in terms of being efficiency and cost effectiveness for optimizing for particular metals versus oxygen production. How important is this to your technology? I know you already touched upon it, but maybe hit upon it.
I think the complexity is in how it needs to be captured, how pure it needs to be, and what form factor it's being delivered to people. Because with our process, basically oxygen's the harder thing to get out and to also condense out and purify compared to the metal products, which kind of come out as a matter of course of doing that. So the cheapest thing for us would be to just ignore trying to capture anything that no one's willing to pay for, treat it as waste, and dispose of it. But then we would add on capture capability for the specific things that each customer wants, whether it's iron or something else. But it doesn't change our fundamental process. I would say it changes our capture and refinement complexity.
Thank you. Also, same question then to Mark before we move on to Achim, Brant, and Elliot. But we only have a couple minutes, so please make it like a 1 minute answer, top high level stuff.
Sure. Real quickly, in the case of hydrogen reduction, since we're looking at a single metal, it's iron, and we've got our oxygen product, so a boost in yield of one is going to yield more of the other. So in that sense, it's a pretty linear relationship. I would say, though, in some cases, for instance, if we're dealing with a high ilmenite feed, then the reduction, the residue after melt refining is going to be high in titania, and that could serve as a suitable feedstock for light metals production.
Interesting. Thank you. In fact, guys, you can also use my question as an opportunity for your last final thoughts on it as we move on to the next session, which basically, Mark, you just did. So thank you. Achim, Uday?
Yeah, okay. Achim, you want to answer or you want me to answer?
No, I can answer. For Roxy, the situation is such that the process extracts oxygen and metals from regolith simultaneously as part of the same process, so that we do not see that there's a competition between the two objectives. So optimization for one objective will therefore be beneficial for the other one. This applies to the extraction of the metal and the oxygen. I mean, another story is the post-processing that we may need to do with the metal to convert it into something that can be used for a specific purpose. So that's a separate question.
Thank you. Brant?
Sorry, I had to unmute. The two big things I can think of is, if we're told by NASA that, hey, we want to prioritize the iron production, no matter what we do in our process, we're going to be making a good amount of oxygen there. But the ilmenite gets reduced a lot faster for us than the silica minerals. So if we were going to tailor our process to make a lot more iron, we would be moving regolith through it faster and not processing a given batch for as long. That doesn't make much of a difference to us, I think. So it's just tailoring it to what our output products are really going to be designed as. The other thing that really I didn't start thinking about this until like this last week here in preparation for this workshop is that silica fume output stream we get. The chemical engineer in me thinks that that's a really attractive way to get silica out of our output products compared to trying to capture it out of that melted slag that we have. I think you'd have a lot less, you'd start with a pure feedstock and have a lot less separation processes you'd have to do. So that has a lot of promise to me, but we just haven't investigated any of that.
Okay.
So if NASA wanted a lot of silicon, we could do work on that.
Thank you. Thank you. And there were a couple of comments in Q&A related that if you hadn't seen them as well. So
okay, I'll check back. Yeah, I'd answered what I could find there.
Maybe you had already. Hey, Elliot, are you still online?
I'm still here, Carl.
Awesome.
Yeah, so we can tailor our process to have higher production of oxygen versus higher production of metals. But the bottom line is you're still breaking apart those oxides. So it has to do with bubble formation and how viscous the molten material is and how quickly those bubbles get to the top of the reactor. And I guess just to sign off here, thank you for this opportunity to talk. And again, NASA, we need that power grid on the moon.
Thank you, Elliot. And thank you all the panelists for excellent presentations and also all the attendees, please stay on, but take a break. We're going on break until 1400, till 2 o'clock Eastern time. So that's 9 minutes from now. Andrea, do you have any words to say, or Athonu, or are we simply on break?
Just one quick thing. Josh Brost, could you please let me promote you to panelist so that we can have you participate in the next section? So that's a message for Josh Brost.
Thank you. So that he can speak, or yeah, so he can present. Okay. All right, then. I guess we're on break. We can sit and chat or whatever we want to do. But I'm going to go on mute for a little while and turn my video off.
Hey, Carl, this is Mark Hilberger. I saw Jerry Sanders put a note in the chat, and I put 2 notes in the chat as well if people wanted to read there.
Can you just summarize it since you're familiar with them? And it's hard to read notes in chat.
Yeah, sure. Well, maybe Jerry would want to discuss his, because I don't understand the context of it. But for me, I really appreciate the presentations. And just to give people a glimpse of what some recent stuff we've been working on, some of our preliminary structural sizing studies for things like truss-based tower assemblies indicates that stresses in these structures are going to be pretty low. You don't have to deal with wind loading, and you don't have to deal with it's 1/6 G and so forth. So what we're thinking is that we may not need in some cases exotic high performance alloys, that we might be able to get away with just simpler byproducts of some of these processes. So for example, we found that essentially a 1 series aluminum, which is essentially pure aluminum, I guess, or close to pure, would work just fine as the material for truss members in these tall towers that we're looking at. So I just want to put that out there. But so the real important thing, though, and I said it in my presentation, was really just to understand, what we would be getting out of the processes. What sort of material properties in terms of stiffness, ductility, and whatnot, so we can then use that information in our trade studies and get a better understanding of where we would need advanced processing and where we could get by with just some regular byproduct material. The other thing that I had was and somebody brought it up in the chat, or one of the questions, Ben Roop, as using slag for things like gravel, and that's definitely something that we had been thinking about, interested in. Some of the earliest roads are probably going to use gravel. Gravel would be a sufficient road bed, and we wouldn't have to do anything too much fancier than that. So considering other ways that the byproducts can be used would be great. And I see gravel as being one of those.
Great. Yeah. Thank you very much. And we said, yeah, it's called mongrel metals or mongrel alloys. So, all right, fantastic. Jerry, are you there? Did you want to have a few comments? Because I still haven't read your chat yet. I hope I don't have to summarize it. All right. What did he say?
He said in the chat, don't only think about single step processes, but I'm not aware of the context of that. It must have been during somebody's talk.
Yeah, I don't know, or my question. But I suppose one could be like, you get a product out from your O2 production and it's something. Well, you could then process that other something again and purify it slightly. Maybe that's where he's going with it, which is very reasonable. Several of the speakers hit upon that as well, potential need for a little bit of further processing, whatever that means. Okay. Well, I'm going to step away for a few minutes.